Hello, everybody. How's everybody doing today? We have a very busy today, and so I'm going to try to go through it as quickly as I can. I don't want to, bypass certain important concepts. I want people to get the idea, and there's a fine line between going fast and covering all the subjects I want to cover today. Anyways, I want to remind everyone one more time we have a conference coming up in Zambia, okay, and that's going to be January, February 2020, okay. So if you plan to go, if you ever wanted to kill lions or whatever, well, maybe this is your chance, okay. Okay, so let's get on with it. The other day I began talking about a couple, father and son team, the Hillsters, and they run a website or an organization called the John, I call them the John Chapel. It's Chapel, but I call them John Chapel because I believe they sell religion. And that's why I call them John Chapel. Anyone in there? Yeah, and I'm in there, by the way. But I don't agree with any of them in there. They're all etherists, 120% of them. I'm going to be discussing that a little bit today. And, um, and they run this site, this organization. And I say that these people, like I argued the other day, they're not doing physics. They're not doing physics at all. They're not even doing science. And so let's get to that. Let's see why they're not doing science or physics. Okay. And here's a little summary, okay, of what problems I find with not only them, but all dissidents of mathematical physics. And the first one is that they don't define their strategic words, those that make or break their theories. And those words are the ones that form the foundations of physics. Things like object, nothing, location, motion exist. They use undefined terms, usually concepts of mainstream, words such as energy, field, wave, plasma, current, vortex, ether, force, charge, mass, time. They usually don't use mass and time. Those are belong more to the establishment than they do to dissidents. They misuse terms, just like the establishment. They confuse straight with rectilinear, infinite. They use that word infinite when they shouldn't use it at all. It's an irrational term, as I discussed last time. They confuse infinitesimal with zero. You know, they say this is infinitesimal when they really mean zero. So they get the best of both words, of both worlds, small and zero and non-existent. They get both with infinitesimal. That's a very key word, so keep an eye out for that when you read or listen out there. They confuse curved with deflected. Um, Solids with space. They use this word solids uh, they use this word space, I'm sorry, as a synonym of solids. And space is something else. Space is what's outside of solids. Okay, and we discussed that the other day as well. And they talk about filled, especially with respect to space, the ether. It's space is filled with ether. They use that word filled when they really mean it's made of, and that's how they treat it. Okay, they move concepts around. And again, we had the case of Ken Wheeler. He moves inertia and counter space around. Others move point particles. And there's a whole host of words that they move around. They're all concepts. Among them, the ones mentioned earlier, energy, field, wave, none of those belong to physics as an object, as a standalone object. There's no object called wave. Anyone using a wave, the word wave as an object, is not a physicist. Obviously, he is not. He hasn't learned the ABCs of physics. Okay. They use the planetary atom. Everyone uses the planetary atom as a given, especially particle theorists, because what else are they going to put for the electron? Particles. And that's what the Hillsters do also. I'm going to go over that today. And they allege that space is made of something. And that's where the ether comes in. All of them say it's filled when they really mean made of. And they never identify the black stuff that gives contour to or encapsulates the particle, the wave, or whatever. And the wave theorists, they're particle theorists. What they're saying is the particles are vibrating up and down. Fine. What's the black stuff that contours each little particle? That's all they have to do. I mean, they think that because they mention a sandbox, that it's, you know, like an ocean, a sea. Yeah, but every little grain there is contoured, is encapsulated by something. We call that space. And they have to identify that and define it or tell us something about space. And they never do. They always skip that question. They say, well, that's semantics, and we don't know what's outside of it. We've never been there, and that kind of thing. And they fail to identify encapsulating medium of space ether. Again, when they mention ether, they're missing that point. They don't answer that. They skip that issue completely. Okay. Um, so here is Bob the Hillsters. He's the father in the father and son team, and he writes in his book some of the foundations, some of the things that he believes serve as the foundations to his book. And the first one is what an object is, which is good. Next one is what is in motion, and the third one is what exist is. And these are the notions that Bob has of these concepts, of these words, okay? And that's how he's going to use them, I guess, throughout his book. And he says, what is real? In my book, Gravity is Not Free, I start with one basic assumption. The universe is made of objects that move. And that's interesting because the word universe means objects and space. And as you can see, he's missed half of the universe there. He doesn't address the word universe the way it should be. Universe means objects in space. Space is part of the word universe, whether anyone likes it or not. And then he says, I define, and that's going to be a problem because he's never going to get to the word space. He's never going to tell you what nothing is, okay? And he said, I define what objects are, what we detect with our senses. And what you read in blue there is essentially the same thing that he synthesized here, okay? I'm not going to read it because I'm going to be moving on today. And he says what instruments detect. He's talking about senses and detect. What is motion? It's a change of an object's position over a given period of time. Okay? And he also says what exists is, he says, that's what I claim is real. Or in other words, what exists. That's at the bottom of it. And he says that's things, he defines motion first. And he says objects in motion. That's what he considers things that exist. Okay? Well, sorry to tell Mr. D. Hilster, but he failed on all counts. He didn't define a single one rationally. Okay? And what's wrong with these definitions? Well, first of all, they're the definitions of ordinary speech. None of them have a place in science, let alone in physics. Object, that which we can detect by the senses. He never figured out that you need another object to do senses detecting. You need two objects. So if God only made one object in the universe, a table, and it's just standing out there in the middle of space, a table is not an object because no one's there to sense it, to touch it, to do anything with it. Is the moon not an object until the asteroid hits it? We have to wait for the asteroid to hit it and say, oh yeah, it's an object because it touched it. Now it sensed it. This is basic stuff. This is kindergarten stuff. And then motion. I mean, what does he say? He says motion is a change. Let's get that back there. He says motion is a change of an object's position over a given period of time. Well, it turns out that change is motion. So he's using a synonym because change and motion are synonyms. And then he's talking about a period of time. Time is a synonym in that sense. In other words, you can't do time without motion. Okay, you can do motion without time, but you can't do time without motion. Time is motion plus memory. Okay, and that's a long story. I'm not going to get into that, but it's clear that if you introduce the word time into the definition of motion, you're introducing synonyms. And yeah, it shows that he hasn't figured these things out. That's what it is. Um, so let me see if I can summarize what the problem is here. Let's see if I can get it here. Okay, these are the differences between irrational, unscientific definitions and the ones that form the foundations of physics. Okay, an object, according to Bob the Hillster, an object that which we detect with our senses. We have see, touch, okay, and that's already requires another object. So we need two objects to define one object. These are definitions of ordinary speech. And again, if we don't sense something, is that not an object? You know, there could be stuff out there like on the other side of the universe. None of those are objects, right? We can't see or touch them, right? We can't detect them. And this is one of the problems that mathematical physics has, in which they want to do everything through experiment. And we don't need experiments to define terms. Any definition which includes an experiment is unscientific. It's an operational or functional definition, which clearly belong exclusively to religion. Motion, the change of an object's position, again, change and time are synonyms. And then exist, objects that move. So an object must move in order to exist. Exist is a static concept. We don't need to move anything to exist. Conceptually, we're not talking again about mathematicians going out there doing measurements and doing everything through experiment. It's a conceptual issue, strictly conceptual. And on the right-hand side, you'll see the foundations of physics. You can compare. We start with a golden principle. Physics requires an object. You can't do physics without an object. Maybe the Hilster might agree with that, but then he doesn't know what he's agreeing to. Something, that which has shape. Okay, and those are the synonyms right under it. Nothing, that which doesn't have shape. Okay, and that's the synonym of space and vacuum. So they're synonyms. And nothing is an antonym, the opposite of something. Okay, so now we can use these words consistently in science, especially in physics. Concept, a word that invokes or embodies two objects, or two words that are treated as objects. Distance is a separation between two objects. Location is the set of distances from one object to all the rest. Exist, physical presence. Physics is the science of existence because it deals with physical presence. Do we need motion? No, we need location. It's a static concept. Exist means an object that has location. If God wants to exist, he doesn't have to be believed in. He doesn't have to be disbelieved in. All he has to do is have location. And before that, he's got to be an object. If he's a concept, if he's intelligence, if he's a spirit, if he's love, then God does not exist by definition for the purposes of physics. He can continue existing in religion. And motion is two or more locations. Okay, so those are the scientific definitions with which we form the foundations of physics. And yeah, definitions are absolutely critical. You can't do physics without defining terms, because what is science? Rational explanations. What is physics? Rational explanations of mechanisms. You got to explain a mechanism. And for that, you need language. I'm sorry, you need language. And you need to define your terms, especially the ones that are going to destroy, make or break your theory, right? Okay, this is Bob's world, okay? And he's got a son, David the Hillster. And it's nice to see father and son. In fact, I have a son too who contributes. He's the boss, in fact. He's the guy who runs this place. Hey, Hans! He's the guy who runs this place, and if I don't behave, he fires me, okay? And, hey, Hans! See you somewhere in there. And so it's nice, and I'm sure Bob is proud of David, and David is proud of Bob. They're proud of each other. And that's good. Hey, This is my boss over
I was just watching this guy. Hey, I'm on camera. Hey.
So he's the boss. He's the guy who runs the shop. Okay, I'm just a peon here. I do whatever he tells me to. Okay, but yeah, I got a great family too. But see, family is one thing, and science is another. And we shouldn't mix them first. And second, the show must go on. Okay, the show must go on, and whomever it might hurt. Okay, so what does Bob's world and I guess Dave's world consist of? Well, they have four particles they propose in general terms. They're still developing their theory. Okay, and they propose the nucleon, and that's an N. He calls it an N1 particle. Fine, and replaces the proton and the neutron. So they're in the nucleus of the atom. The G1 replaces the electron and the graviton and the photon, right? So these are the critical ones that they're going to do their theory with primarily. The G2 is a force, a particle that is a force. Now, where did I hear that before? Okay, and they say there will be more particles. They threaten us with more particles. Okay, so we're going to have more particles coming up, from their view of the world. Okay, so what kind of theory did they propose? Well, they proposed that the G, especially this G1 and G2, G3, N1 and N2 particles, and so it's a particle world. Okay, it looks, in my opinion, this I'm just going by what they say. Maybe I'm wrong in what I'm presenting. I don't want to misrepresent them, but I'm just going by what they say. They say there's G1, G2s, N1s, and N2s. There it is. That's what I put last time. Now, I don't think I'm misrepresenting anything here. And the issue here is, what is the black stuff? And of course, since Bob the Hillster does not believe that the universe includes space, just includes matter, he's not going to define what that black stuff is, or deal with it at all. Apparently, I guess he doesn't care about it. And so, yeah, I've got a little bit of problem with that, with him skipping over space. Space is what the big problem is. Okay, and so what are the problems with what they propose? Okay, well, this is what I have synthesized as far as what I can tell. There's probably a couple more problems, but this is what I'm going to cover today. Oh, sorry, got the wrong one there. But essentially, those apply to them anyways. Those do apply to them. See if I can find it here. Where is it? Here it is. Okay, these are the problems that I see with their theory. Okay, first they invoke the ancient ether, and Dave disagrees with me. He says that I'm misrepresenting them, and no, I'm saying I don't. I mean, they're as far as I can tell, this is what they're proposing. Okay, this is what um, they're proposing this little thing here. Where is it? They're proposing particles. And there's your ether next to it. Now, mine's in motion, okay? It's already in motion. But they're going to set their particles in motion as well. So in what way do their particles differ from the ancient, well-tested ether? I mean, they've got a particle theory. Well, what's the background? The background is black, just like, right and left are the same thing. And all they have is a bunch of particles. So they color-coded them, and they say, well, this one's the G1 to G2, fine. And then how are they going to run their light and their gravity, especially? Well, they're saying that the G1 does it all. So all those white ones, you can consider them, for the most part, G1s. And some of them vibrate up and down, and others go straight. The ones that go straight are gravity, and the ones that vibrate up and down are going to be light. That's what they're proposing. I'm not sure in what way I'm misrepresenting what they're saying. So I don't know. Again, I try to go by what they write and what they are saying, so I cannot see how I'm misrepresenting them. And let's see if we can. So this is their ether essentially. This is the problem. The problem is that I say they propose an ether whether they like it or not. I'm just telling them what they're saying, And you see on the left-hand side, you got a finite ether. They're proposing the infinite ether. They're saying that there's just a bunch of particles and we don't know where that ends and we don't care because we have no way of testing it. I guess that's their reasoning because that's the reasoning of the establishment. And so they don't care about where it ends and they don't care what encapsulates. They don't want to deal with those issues. Okay? And so I see that as a problem. And this is essentially, as I see their universe, just a bunch of particles moving. Now, one of the problems that we have there is that they're saying that this their particles travel straight. I can even imagine their particles traveling straight there. See here, let's see if this is the right one. No, wrong one. Keep putting that same one up there. Where is it? Down here. Got so many of these that it's unbelievable. No, wrong one again. Where did I put it? Well, I can't find it now. Oh, here it is. No, that's. I can't find it. Okay, let me just continue. Anyways, I can't see a straight line there. Okay, and I put a baseball in there and see what happens with this. According to the Hillsters, we have particles running straight into the baseball, and and the blue and red are the same. I'm just showing blue and red as directions only. They say as soon as they hit an object, they scatter. Okay, a lot of them scatter because they hit atoms. Okay, so we're going to be hitting atoms that are going to scatter, and some go right straight through and go out the other side. So we've got a little bit of magic there because they don't explain why or how so far. Maybe they will in their book or whatever, but right now they don't explain how these particles, some of them go through and some interact. I guess they go through the interstices. I guess that's what they're referring to. I don't know. But that's how they get concentrated in the center of the ball, and that's what they're going to call, that's what they're going to call gravity. Okay? So what's the problem that I see with this? Well, you got particles coming from every direction, so I cannot imagine anything traveling straight to begin with. Okay, and here I put a little circle next to it. This is a region of space next to the ball. And, particles are coming to that region also from every area of the universe. And the question is, do they form atoms? I mean, aren't we going to have atoms formed in there somehow? And so I got a problem with this because, all these particles are coming in there and just going through in that region, and there's nothing to stop them, they claim, and that's why there's no gravity in that region. Okay, but then we have to find out how an atom forms because they're saying that the atom is made of G1 and G2 particles and the nucleon as well. So they're saying, let's see if I can find it here again. Is this the one? Yeah, they have all these particles there, right? And so those form the atom. And so the question is, how do all these particles, which are going to be used as gravitons, as photons, as electrons, and they're moving into the ball, they're stopped by other atoms that are made of the same stuff. Well, why don't atoms form spontaneously in the middle of space? In other words, how did atoms form in the first place using their particle model? What was the mechanism? And this is one of the things that I see wrong with it. Okay, I do have a little bit of problem with this idea that they're proposing. Okay, let's see. Here's the summary of some of the particle problems that I find. One of them is this: the fact that they invoke the ancient ether. The other one is that they're saying that they're infinite. Their ether is infinite, or they don't put a boundary around it. G1 travels straight. I cannot imagine that in a sea of particles that are vibrating, and how they can distinguish one that waves up and down becomes the photon or the light, and the other one becomes the graviton, goes straight in a sea of particles. Well, I cannot picture that. I'm trying to picture that, but I can't. So they must be more intelligent than I am, and I'll concede that if they can show that's the case. Then we have the problem of accumulation of particles, and this is an interesting thing because they say everything goes inside. More particles come into an object than come out, and that happens with every object in the universe. So no object in the universe is really sending more than what it receives. It's receiving more, more and more particles. So these particles should be exploding. I mean, they should be filled with particles. We should be getting heavier every day because particles are just coming into objects and to the center of gravity of every object, and fewer are leaving. So I think that's a fatal flaw in their system, completely fatal. I don't know. I don't know how they're going to answer that one, but in their book. But okay. Uh, and one of the things you look at is, before you read a paper, you usually read the abstract, and you look at the abstract. If it makes sense, you say, "Oh, I'm going to read this article." But if you see only nonsense or you see so many fatal flaws in the abstract, then you don't read the article. And right now, the abstract that's out there for their particle model is lacking. And I'm being kind, okay? It's lacking. They use the planetary model because what are they saying? They're talking about the N1, the G1, and G2, and they form the atom. What atom are they talking about if they're talking about a particle model? Well, obviously, they're talking about Niels Bohr's atom, the planetary model. And and we know that doesn't work because the big problem with the planetary model is this. This is, as far as I can tell, this is their atom. They're saying, look, we have the G1 is the electron. The G2 is the binding force. I like that one because a particle is a force that they criticize in one place that's saying that force is not an object, and then they turn the particle into a force and treat it as an object, the word force. Okay, fine, let's skip that, but the nucleon is a particle for sure, and the G1 is a particle for sure, and if what we have is particles called G2s, whatever, let's forget about the word force, let's just concentrate on the particle, we have discrete particles. And so we have particles, particles, particles. What is the black stuff? We need to find out what the black stuff is. And here we have a second problem, which is how is the purple ball attracted to the red ball? What keeps it there? Why doesn't the purple ball keep going and fall into the nucleus? Why doesn't it fly away? What keeps it in the orbital area? Okay, because they talk about that. The G2 particle is the orbital of subatomic atoms. And orbital is a bunch of orbits. That's what an orbital is in quantum mechanics. And they're going to use that word. They better know what it means. And it means a bunch of orbits. And you don't construct an orbital, a region, in other words, a membrane with orbitals. And that's what quantum does. And they're doing the same thing. They're going in there and they say, oh, yeah, we construct our orbital with itineraries, with trajectories. Oh, great. So I have a problem with that, a lot of problem with that. And so let's compare it against the rope model here. Here's their model as I see it again. I don't want to put words in their mouth, but I have to go by what I see out there. Maybe I'm misrepresenting them. All I can do is tell you what I understood from what I read and what I've seen and heard from their videos. And again, you see my model on the right, and that's the rope. It's made of two twined threads. One thread turns into the electron shell, which curves around the proton star. And what you have there is the up and down, the pumping of that electron shell, and that's going to be the Bohr's quantum jump. Okay, that's what's been mistaken for quantum jump. And by going up and down, it torques the rope and it sends that signal along the rope to another atom. That's the model in a nutshell. And my model is like the one used in chemistry, which is this model you see on the lower right there, which is, they call them orbitals. No, they're not orbitals. They're balloons. They're membranes. They're things. And if you compare it against the Hillster's atom, which is the quantum hydrogen atom. We don't know what that how the proton is attracted to the electron or why the electron doesn't fly away spontaneously. That's what they got to answer, or whoever proposes a particle model. And this is I think a fatal flaw also. Right? Um, and again, the fact that that more particles enter the atom, the atom or the whatever object you have in there, that's already quite fishy. But then they have a big problem because we have the what I call spaghettification. I don't call it. It's this is the term from the black hole guys. If you heard it some ever, you'll see something that looks like this. Let's see if I can find it. Where is it? Spaghettification. Here it is. And it looks something like this. This is how they illustrate it. And that means if you fall into a black hole, and here all I'm saying is I'm not talking about black holes. I'm not proposing black holes. I'm saying that you fall feet first into a hole, into a what is it? Center of mass. Okay. And your feet get dragged faster or first before your head. That's the point here. The point is that your feet are closer to the center of the earth than is your head. That means that your feet are accelerated at a faster speed than your head is. Here you see another vision of that. Here's the astronaut. He's standing, on the earth, and his feet are closer to the center of gravity. Therefore, this 9.8 meters per second square, what does it mean? It means your feet travel faster towards the center of of the earth than does your head. Well, why am I mentioning this? Well, because apparently the Hillsters failed to notice something which I think is totally fatal in their system. And here it is. Let's see if I can find it again. Okay. Give me a second here. I'll get it. I just got so many of these that it's unbelievable. Okay, here it is. Okay. Here's a ball falling to Earth. A baseball is falling to Earth. Okay. So what do they say? They say the ball is being pushed more by the evil red forces than by the blue ones that come out of the Earth. That's their model for gravity. The ball is falling because there's more forces, more particles, not forces, particles hitting the ball from above, in this case, than from below, from the center of the Earth. Okay, that's their model. Okay, so why don't we modify this a little bit so we find what the problem is with this? Okay, what we're going to do, we're going to put a black ball in there now. Okay, we're going to put a third object in there. Okay, and so what happens now? If the Earth wasn't there, we know the two balls get closer to each other. The distance between them decreases. Now we put the Earth, and they both fall to Earth. That you can say they fall as a system. But the baseball, it's going to also move in the direction of the black ball. And I don't know how many of you know phase velocity within a wave. That means that the wave within the wave has already a motion. And this is more or less the same concept. You have the baseball falling down to the center of the Earth at 9.8 meters per second square until you put the black ball. Once you put the black ball, now it pulls on the baseball upwards and it slows it down. So the baseball should travel slower than 9.8 meters per second square. Okay? So I see a problem here. I see serious problems with what they're proposing, and I'm sure you can't do you can't do physics with particle, let alone gravity. I mean, it's just that they've been trying to do gravity and light since for the last 10,000 years with particles and waves, and it just don't work. And they never give up. Okay, so let me just go over a little thing here that I think is worthwhile if you want to learn something today, which might be of interest to you. You heard of the gravitational constant G. Do you think that the Hillsters know what the units of the gravitational constant G stand for? Well, not a single mathematician on earth knows what they stand for. See, they were put in there by hand because they had to match the equation. Now, okay, Cavendish did his experiment, right? And he had the torsion balance, fine. But then the units are just because they match the equation. They were put in there by hand. You memorize them in high school because you're told to memorize them for the test. You pass the test and you forget about it for the rest of your life. Nobody deals with it. No one is researching the gravitational constant G, and I don't mean, they look for the value. If the value is exactly what's been measured, we don't care about the value. What do the units represent? What does it mean in physical terms? That's physics. The rest is garbage mathematics that has nothing to do with physics. You got to tell me what the units stand for. That's physics. That's mechanism. Okay? You got to tell me what the mechanism is. And they can't. Well, what if I told you that I can? I'll tell you what they mean today. You're going to learn something. You don't have to believe in me. I never ask you to believe. I ask you to understand, okay? I want to make that clear. I'm going to show you something. You judge for yourself whether it's good or not for you. All I'm interested in is that you understand. I'll make that clear up front. Okay, let's see if we can understand the gravitational constant G and what it stands for. Let's put it up here first. And don't get scared because of the math. Okay, please don't get scared because of the math, because the math is not so important to a certain degree. Okay, I want you to understand it conceptually. Okay, so don't run away because you see some math here. Okay, if you're not familiar with math. Okay, let's go slowly. Okay, let's go slowly for those people who are not so fast in math, etc. We have force equals, this is Newton's equation, gravitational equation. Force equals gravitational constant G times mass divided by distance. Distance square, I forgot the square, sorry. Error on my part, but yeah, it's distance square. But I'm not going to deal with the mass distance square. I'm going to do only the gravitational constant G. Okay, what does it equal? It's equal to that number, 667 times 10 to the minus 11 Newton meter kilogram, blah, blah, blah. Oh, that's so hard. What does that mean? I mean, if someone told you it's 10 seconds, you know what the seconds mean. You know what those units mean. Someone tells you 10 meters, you know what that means. Someone tells you 10 kilograms, you know what that means. But what does Newton meter kilograms mean? What the hell is that? And now the Newton, which is that N on the right, is kilograms meter per second. So if you multiply the numerator, meter squared, times kilogram meter, you get what you see on the bottom in the numerator, kilogram meter cubed. And if you multiply the denominator, the bottom part, right, kilogram squared times second squared, you get what you get on the bottom, kilogram squared, second squared. Okay, so that's what all the units that involve the gravitational constant G. That's 667 times 10 to the minus 11. Okay, that's the number. Okay, and you say, well, what does all of this mean in physical terms? That's what we're trying to figure out here, okay? And again, try and make this as simple as possible. I'm going over it several times so that people understand what's going on here, especially those who are not so familiar with math. Let's go with the interpretation, the physical interpretation for the gravitational constant G that no mathematician on earth will tell you what it is. Go to Harvard, go to Cambridge, and put them on the spot. Tell them, hey, can you tell me what those units mean? What does that mean in physical terms? Let's see what the bozos over there tell you. Okay, here it is. Let me show you what we've got here. Let's multiply that number that you had before, 667 kilograms meter cubed, 10 to the 11th, kilograms squared, second square. Let's multiply it times 1. 1, you got 9 times 10 to the 16 over 9 times 10 to the 16. It is fair in mathematics because that equals 1. So you're just multiplying the whole thing by 1. What do we get? Well, we get 0.74 over 10 to the 27th. Big number there, right? And that times the speed of light. 9 times 10 to the 16th meter squared, second squared. That is the speed of light. Okay? Because you scratch out the two squares, you get meters per second. Okay? Okay, so what do we have here? We have the speed of light times that unit, times that whole thing that you see in the square. Okay, let's continue. What do we have next? Well, now we can factor out the mass of the hydrogen atom. we have 90% of the universe is hydrogen atoms. About 10% is hydrogen, and there's maybe less than 1% that's all the other elements. But all the other elements are made of hydrogen atoms. For example, you take the uranium atom, 92 is the atomic number. That's like saying, 92 hydrogen atoms. So we can deal with this whole thing as hydrogen atoms. We take the hydrogen atom, which is measured at least to 1.67 kilograms over 10 to the 27, and lo and behold, the whole denominator disappears completely. And all you're left with is 0.44 meters over a kilogram squared, and I'm not going to analyze that here today, times the velocity of light squared times the hydrogen atom. Why? If you look on the right, you'll see why. Because all atoms in the universe are interconnected, and light goes from one atom to all others, and all others to our atom. That's velocity of light squared. That's what c squared means also in Einstein's equation, E equals mc squared. Okay? Now, that's my explanation, and I have a physical interpretation, as you can see there. So, ask them to define these things for you. Okay? Okay. So, what's next? Well, what's next is I wanted to do a little of, magnetism. I discussed that the other day. Okay. And let's see what we have here. Well, we have our, what I call the troika. These people who do dissidents. They're the kings of dissidents. Okay, we have on the one hand Ken Wheeler. He does things with undefined concepts, and that's the problem with his version of physics and of magnetism. We have Thornhill. He doesn't even do magnetic attraction. He can't explain it at all. And then the Hillsters, and I'm going to go over their part in a little more detail. But let's go with the first two first, just to get them out of the way. What does then Ken Wheeler do magnetism with? Let's see if we can figure this out. Okay. Let's see. Got so many of these. It's just they should find a better way of doing all these things. Okay. Here we go. Let me put this here so I can find it easier. And Wheeler uses definitions that he never defined. He uses words he never defined. One of them is, like I discussed a couple weeks ago, his dialectricity, and all these words that he uses. Well, what does all that mean? Well, if you look it up, dialectricity is, essentially, he says, dialectricity is counterspatial, and the ether is counterspace, so they're all these words are synonyms as far as he's concerned. And he never defines any of them. Not one of the three does he define. And he says their dialectricity is the ether under stress or strain. And that definition already tells me that it's a dynamic concept. So he cannot say that dialectricity does this or does that. He can't say that because dialectricity is not a physical object you can move around, and that's exactly what he does. So no, cannot explain magnetism because he hasn't defined these terms in his book or online for that matter. He just goes what is dielectricity? Well, we all know what dielectricity is. We learned this stuff in kindergarten, right? So we know exactly what dielectricity is, and that's part of the problem. The problem is that they get away without defining words. And they're going to be doing their physics without defining these terms. And that's exactly what Ken Wheeler does. Okay, how about Thornhill? Well, Thornhill doesn't do much better. In fact, he does worse, I guess, in a sense, because Ken Wheeler at least tried to give it a shot. But Thornhill, he talks about electricity and magnetism, what is called as electromagnetism. And I went through his site, and I went through two sites, the Thunderbolts and the Electric Universe. and you won't find anywhere in there. And I challenge you to do so because I went through there looking for it. I really looked for it. I couldn't find it, but maybe it's there somewhere. I don't know. Maybe I just missed it. How a magnet attracts another. You would think that a guy who says, look, we don't do our universe with gravity, we do it with electricity and magnetism, as a minimum would say, look, let me tell you how a magnet attracts another. Let me show you that I understand and know this stuff and can explain it to you. And then he can go out there and say, and now this is how stars work through electromagnetism. Well, you won't find it anywhere. And here you can go to a book that is available online. You don't have to buy it. It's this fellow. His name is Finlay. And I'm not going to read all that. I'm just going to tell you three things, and they're in green, blue, and brown. Okay, and you can see I put some headings there. One is direction, the other one is strength, and the other one is polarity. Those three uh, descriptions. They are not explanations. So these people begin, and this is in the section about magnetism, and all they do is describe it. They say, look, this is the direction of the magnetic field. And this is the strength of the magnetic field. And at the bottom, they reinvented or resuscitated Peter, what's his name? Peregrinus. And which in 1269, he said, north attracts south and south attracts north. He's the first guy who documented that. And that's essentially where these guys are today. They haven't made any progress whatsoever since the days of Peregrinus. Okay, how about the Hillsters? Did they do anything better? Well, let's find out. I have three problems with what they say. The first one is that they build this perfectly, smooth cocoon, which is going to encapsulate the magnetic field. The magnetic field is made of G1s. Okay, that's what goes around the magnet through the center and then out and through the center. Okay, and it goes on the bottom as well. Think of two. I always use that analogy because it's a good analogy. You think of two army tanks, and they're upside down. One with a track against the other track, and that's essentially what they do. They roll around like that, like if two tanks are facing each other, track to track. Okay. And that's essentially what they're saying. They're saying that rolling around is particles, G1 particles going around. Why don't they leave? Well, they don't leave because they are constrained in there. The magnetic field is molded, is contained by the flow of G2 particles that are hitting the magnet. And again, they have this problem where they say some particles go through and out the other end, and other particles go, in the opposite direction, and they end up all primarily in the center of mass of the magnet. And so they think that magnetism is essentially a gravitational phenomenon. In other words, it's gravitational because it's gravity to where all the particles are coming to. In other words, they're not pulled by gravity as some might think. No, that's not what they're saying. They're saying the particles go through, most of them get scattered, some go out the other end, and then the same thing happens in reverse and from every direction, and you end up in the center. That's how they end up with a center of mass. And they say that, it's this field out there that is constraining, the magnetic field, the so-called magnetic field. And what can I say? Ptolemy would be very proud of them. So let's see it. Let's see it in motion. Let's see if we can see what these people are saying. Let's see, now that I more or less describe what they're saying. Let's see if we can visualize this thing. Okay, this is essentially what Bob Hilster, the Hillster, is saying. He's saying attraction G1 flows through both magnets. The G1 flow through both magnets are in the same direction, which minimizes the repulsion. The G2 force around the magnets are stronger, and therefore the magnets move towards each other. In other words, the little dots that you see out there, that's the G2 particles. And the G1 particles are the ones that make up that brownish, beigeish color that, there was a magnetic field, the typical magnetic field that surrounds a magnet. So those are G1s, and the ones on the outside are G2 constraining them there. That's how it is, in their model. And then repulsion, well, if you turn it around, I haven't illustrated the repulsion, but they say the G1 particles flow out the south end of each magnet, causing the G1s to hit head on. Okay? And so again, the magnetic field is constrained by the G2s. Okay, so that's important to see in their model. Now, the first problem I've got with this is, again, the G2 particles are magical in this case because, we're the G1 particles out there in space. So they put G2s, and we're the G1s. I thought G1s also cover all of space. That's one issue. The other issue is that, I don't see anything traveling straight here. And they insinuate that, whenever they need the straightness, they'll go with straight, and then whenever they need the curving ones, like for light, they'll use the curving ones. And that's quite ad hoc, in my opinion. I don't see that model working at all. But why does he do this? De Hilster is trying to do the following. He makes this drawing of his forces, and you can see the force in red there, F2. That's a force, okay? And so that's what he's saying. He's saying what's outside of the field line is the G2 particles. That's the force that he's talking about, okay? So that's important to keep in mind. And what's flowing around are the G1s. Why does he do this? Well, he does this for a given reason. See if I can find it here. There it is. Okay, oh, that's my drawing. I put it in red. See those lines to make sure that you understand it's not a force like in quantum mechanics would put it as a force. No, they're saying these are particles, and they're turning those particles into forces. Let's make sure we understand that when he says force and he draws that little red line, and I just extended them with particles, just that make sure that you understand that those are particles that are hitting the magnetic field, which is made of G1s, okay? Now, why does he do this? Well, he does this for this reason. This is the typical magnet that you'll see, the flows, okay, in a magnet. And but this is not what they're suggesting. See, because all that seems like so perfectly done and so on. No, what they're suggesting is something that looks more like this. Let's see if I can get it up there. Okay. See, you got to look at this as a bunch of particles hitting the magnetic field, and the field is made of those, I hope you can see those orange ones. Are going from, in the top, they're going from left to right, from west to east, and in the bottom, they're also going from west to east. In other words, they're going towards your right. And they're going around through the center of the magnet out and back out through, what is known as the North Pole, okay? What constrains this perfectly symmetric and perfectly smooth field is a bunch of particles which are sputtering this whole field. And see, they treat that as something perfectly uniform, because again, they're thinking of an ether, and then they deny the ether, but that's what they're proposing essentially. They're saying a bunch of particles are hitting the field, or are hitting the G1 particles, which are not allowed to leave. And so the G1s just keep rolling around because of gravity in the center, right? And remember, gravity is the flow of these particles going right through the magnet, okay? And you could draw a line from the center of the magnet to everywhere on the universe, and of course that would be the center of gravity of the magnet. So they're doing this with gravity, okay? Okay, one of the problems we find with all of this is that all the particles, remember in their model, all the particles go to an object. And so, the magnet should be receiving more and more particles every time, more than what it shoots out. And so the magnet should be expanding like a balloon, all of these particles from all over the universe coming onto our magnet, and fewer leaving the magnet, and that's happening to every object in the universe. Well, again, we have a problem, because all objects should be increasing in mass and getting bigger or whatever, and that's what his model suggests, at least as far as I can tell. I don't see anything else. Okay, so once again, why does the Hillster do this? Okay, let me tell you why. Here it is. he's only trying to mimic that. He's trying to show you, okay, he's trying to show you that he, with his model, right, he can tell you why the shape of the magnetic field looks like that. And what's he doing? He's taking a static field. So he said, look, if you sprinkle iron filings around a magnet on your desk, those are the patterns that you will see, and I can tell you why. He says because you have all these G2 particles hitting the G1s, which are all those lines there, and they don't let them come out. Essentially, okay, they're constraining the G1 particles to go around the magnet for I don't know what reason exactly. Okay, so what is the problem with this? Well, let me show you a couple problems. The first one is this one, and that's that here you can see the arrows that I've drew for his magnets. What I did was, I just took a little bit of the noise out of his drawing, just cleaned it up a little bit, and had the G2 particles still hitting the magnets. And you can see when the two magnets, they're both facing north-south, okay, so it's going to be attraction here, okay? And you can see that the particles coming from the lower, for example, southeast, the one in red there on the top, they're hitting the edge of the magnet, which is blocking it or shadowing it from reaching the particles that are supposed to push the gravitational field of the magnet on the left, and vice versa. The blue coming from the southwest is blocked by the edge of the magnet, because this is a magnet. He did it with a coil, but this is a magnet, okay, essentially what he's describing. And they're hitting the edge of the magnet and not allowed to push the G1 particles, okay, that go around the magnet on the right. And as you get them closer and closer, you can see that it gets worse. The free flow of particles is interrupted by matter, by atoms, which form the magnet itself, and they do not do their job. Their job is to push the gravitational field, the G1 particles, around and into the magnet and out the other end. And here they're being blocked. Okay? So that's one problem. Let me tell you a bigger problem still. And this is this one. I'm sure they cannot explain this at all. Okay? And that's this one here. And that's when you put a magnet underneath the water, okay? The magnet pulls one iron filing at a time. I cannot imagine this being done gravitationally. I cannot imagine Mother Nature throwing one particle or a bunch of particles at the iron filings, pushing them inwards one at a time, like it's done here. You can see it's gradually being pulled towards the magnet. They claim it's push, okay? And you can see they don't line up in the center, as they claim. They line up at the edges of the magnet. So I think they got a couple of problems with their model, and again, I had to go through with this kind of fast. I wish I could have gone a little slower, but I'm going to take another 15 minutes here just to show you something that you can compare it against, okay? And the first thing we should note is this, okay? And that's that, how all these people have done pull over the years. Let me open this up a little bit so you can see it better. And there it is. And these are the different proposals that people have had over the years. We have quantum. They use negative momentum transfer to pull on the donkey. Okay, they throw stones and they pull it inwards for whatever reason. They just put a negative sign in the equation, they're done. Very easy. Relativity, they use warp space-time. And so, if you want to pull the donkey towards you, all you got to do is slide along the warpage of space-time. We're done. Easy stuff, just field equations. How does the Hillster do it? He does it the Casimir way. He wipes out the particles in between, essentially. What he's saying is there are fewer particles in there. Fine, that's you just think of it that way if that makes any difference to you. And then the donkeys pushed towards Casimir there, by the particles behind them. And again, all I can say is Ptolemy would be proud of the Hillsters, how they do their physics. And no, the way we do it in science, in physics, we use a rope to pull on a donkey. Very simple, very Occam-like, we use a rope, okay? So how does physics do magnetism? Let's find out. See if I can get it in there. And again, and let's quickly go through it so that you can see the mechanism. I just want you to see the mechanism so you know what to compare against, okay? And here you have axle and rod, my two good fellows. I'm saying the threads, not the rope, the threads. Here I'm using ropes, but in the model it's threads. And people sometimes don't understand the difference between a thread and a rope. There's two twined threads to a rope. And what do we have here? Well, we have axle on the top, on the upper left, and rod on the upper right. And in the case of attraction, you can see they're swinging their threads around, their ropes around in this case, and they latch onto each other, and that's the mechanism of pull. Now you see a mechanism, a physical mechanism. I don't care if you believe in it or not, I just want you to understand the mechanism. At the bottom, we turn the first guy around, and you can see that now the ropes are clashing against each other and they push each other away. Okay, how does this relate to a magnet? Let's find out. Let's see if we can figure this out. Here it is. Okay. Again, this is the mechanism of attraction. You have counterclockwise on the both upper halves of a north-south magnet, and you have clockwise on the bottom, which is essentially what the Hillsters described, which is true. That is the flow, and as we know by the water example, yes, magnetic field is something in motion. In fact, both James Maxwell and Michael Faraday both said, look, there's matter in motion. That's what those field lines are. We just don't know what they are. And I'm telling you now, those are threads. The threads are moving around. They're going through the south, into the south, out the north, okay? And they latch on to each other. The top with a top and the bottom with a bottom. That's what's happening from a physical point of view. That's the rope model of attraction. Now let's look at the repulsion. We're going to turn one magnet around, okay? Here it is. Here's repulsion, okay? Okay, now you see why as soon as we turn one of the magnets around, now the top is clockwise on the left and or was it, yeah, well, the point is they're facing each other now south to south. And so one is going clockwise, the other one is going counterclockwise. Same on the bottom, it's opposite. You have counterclockwise on the left and clockwise on the right. And bottom rejects bottom, top rejects top of the magnet, upper half. Okay, so we have a mechanism, a physical mechanism that you can visualize. Whether you believe in it or not, that's a separate issue. I'm just telling you I have a mechanism. And if someone can give you a mechanism, that would be great. And here's a summary of those two things. You have to watch it a little bit because, let's see, we got to do it this way. Okay, here it is. Okay, you can see what's happening there to these, I erased it. Here it is. There it is. I'll just step aside. In other words, what you have is repulsion, and this is in motion. You can see they're hitting each other. And now we turn it around. We're going to turn the magnet around, the one on the right. It's going to go, what, counterclockwise, right? So watch it. There it goes. First we turn it, first we turn it in the same direction to show that nothing changes. Now we turn it counterclockwise, and now we have repulsion. Okay, so they hit each other. Threads push against each other. Again, attraction. They attract each other because they're both going clockwise on the top. They're both going counterclockwise on the bottom. That's what's happening. All right? And you got to, all I'm asking is you understand. I want to make sure that that's understood, okay? You understand the mechanism I'm proposing, okay? So with the threads, yeah, we can do it, okay? And unfortunately, I had to rush it through, but maybe another day I can go a little slower on these. Anyways, you can see my objections to the Hillster, both gravitational theory and magnetic theory. And I do have something to propose in exchange, and that's the rope model. All atoms in the universe are interconnected. That explains action at a distance. Gravity is pull. It's not pull, really. It's drifting in space. Objects drift towards each other, okay? Uh, you know, space doesn't stop them because space is nothing. And so they drift towards each other. What? Because they're connected by ropes. As the object approaches another object, the ropes fan out. Very simple system. Mother Nature is a very simple lady. She doesn't run her universe in a Ptolemaic way. Magnetism, they both go in the same direction and they pull. They both go in opposite direction, they push. We're done. Again, simplicity, symmetric. The rope is a simple and symmetric object. How much more simple and symmetric do you want it than this? Even the motion is symmetric. When a rope turns, in other words, when it torques, the signal is felt by the two atoms at the opposite ends. With that, I'll see you, on Sunday, and we'll continue with this line of thought. Maybe I can fill in some of the gaps. If you have questions, please put them up there. I'm going to look at them. I don't answer in the sites, okay, but I do. If some people ask good questions or whatever, then I'll bring them up. I don't elude questions. If there's an interesting question, I put it up there. Questions that I don't answer right up front, because a lot of people want to know certain things. What are the ropes made out of? They want to know how ropes avoid tangling. They want to know if the rope extends all the way from here to Andromeda Galaxy. They want to know how much the rope weighs. All that stuff is in the book. Why is it in the book and not on the internet? Because I want to sell books? No. It's in the book because 99% of the people out there don't understand the foundations of physics. And you won't understand my answer to your questions unless you learn baby stuff, unless you learn what an object is. People don't know what an object is. People don't know what the word exist means. And you got to go through those steps. And it takes 2 years to understand what an object is. 2 years for a mathematician to learn what an object is. That's how difficult it is. Some people think hologram is an object. They don't know if God is an object. They can't tell you whether an angel is an object or a concept. And we get to all those intermediate, those that are on the fence, and we got to resolve those. We got to know what an object is for the purposes of physics. And for sure, plasma is not an object. Electricity is not an object. People say, "What do you mean? What are you saying?" Yeah. So if you don't understand all that, I can't tell you anything about why the ropes avoid tangling. You'll never understand anything. And just to mention one more thing, just to give you a hint why it's a difficult question for you to understand, not for me to explain. I can explain it, but you won't understand. Think of the word touch, which is a good example. And you say, well, touch, we all know what touch is. I touched my finger, right? Well, did you? Did you touch your finger? You say, sure, I did. Look, I touched. Well, that's in ordinary speech, not in science. In science, we define touch, and we have to define it stringently, rigidly, rigorously. And we say zero distance. And you say, okay, zero distance, touch. Okay, I can understand that. But when you have zero distance, you've turned two objects into one, and touch requires two. So what am I saying here? I'm saying that before a rope can cut across another one, it's got to touch it. And you first need to understand what touch means. I'm not going to spend a whole year explaining on the internet what touch means. And that's what people would have to understand. They have to understand the language of physics. They have to know what an object is. They have to know what exist means, what motion means, what distance and location means. They never define these words in all of mathematical physics. And those are the foundations of physics. I'll see you on Sunday. We'll see you then. Bye-bye.